everyone, welcome back to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss magnetism and matter, medium important chapter. 3 questions comes from this chapter, and it is a very small chapter in terms of overall coverage, but in terms of information, this is an information loaded chapter, so lots of information is there at one place, but they are relatively easier. So we will try to complete this chapter as quickly as possible, and if you are watching this series for the first time, then definitely you have to subscribe to our channel and definitely give this video a thumbs up so that we get the motivation to make more and more videos. So without any delay, let's start with today's lecture, that is magnetism and matter. So first let us look into the all important concept from this chapter. What are all the important concept from the chapter? So if you are revising the chapter just before the exam, you have to definitely look through this important concept. What are all those? Bar magnet and solenoid, the basic 2 types of magnets, that is bar magnet and solenoid is basically electromagnet. Now what next? Magnetization, another important concept from this chapter. Next we have magnetic field intensity or magnetic intensity H. Okay, that is also important. Next we have magnetic properties. We have different properties: diamagnetism, ferromagnetism, paramagnetism. So these are the important properties of magnets. So these are the most important concepts from this chapter. So first we will start with the bar magnet. So bar magnet is basically the earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to north. So approximately it starts from the south pole, goes towards the north pole. It exactly not like that. There is slight degree of angle with associated with it, but those parts are not on the syllabus. So we will assume that in the ideal world that magnetic field of Earth's north pole is located exactly at north pole and south pole is located exactly at the south pole. Now when a bar magnet, so bar magnet is basically, you have done some experiment in your lab, it's looking like a bar of ice cream, right? The same thing, a solid bar, so but it's in a smaller size. Okay, that is why it is called a bar magnet. The shape is called bar. So the bar magnet is freely suspended. It would point to the north south direction. So basically if you suspend a bar magnet, after some rotation it will eventually make static, and one end will point towards the north, one end will point towards the south direction. Okay, the tip with which points to the geographic north is called north pole, and the tip which points to the geographic south is called south pole of the magnet. So after it comes to rest, if suppose this end points towards the north, geographic north, then I will say this is north pole of the magnet, and if this end points towards the south of the geographic south, then we call it south pole of the magnet. So the name of the poles comes from the fact that when you suspend it on the earth, then it points towards particular direction. That is why it is, the name comes as north pole and south pole. Okay, now what else? There is a repulsive force when 2 north poles or 2 south poles of 2 different magnets are brought close together. So if you have a north pole from one magnet, another north pole from another magnet, okay, if you bring them together, then they will feel a force of repulsion, same as charges. So similar charges repel, okay, and unlike charges attract. Similarly here, like poles repel, unlike poles attract each other. Conversely, there is an attractive force between north pole of a magnet and the south pole of the other, similar to that of the charges. Now let's move on. We cannot isolate the north or south pole of a magnet. If a bar magnet is broken into 2 halves, we get 2 similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles, known as magnetic monopoles, do not exist. So in in the electric charge chapter, we have learned that there are 2 types of charges: positive charge and negative charge, and they can exist independently. So you can have a negatively charged object or you can have a positively charged object, but in case of bar magnet or in case of any magnet, basically you cannot have isolated poles. You cannot say, okay, I have only a north pole, or if I have only a south pole. It is not possible. Magnetic poles always appear in opposite pairs. Okay, so either you will always have a north pole and south pole together. Even if you try to break it and make, say, okay, I have a bar magnet, okay, and I want to break it into two halves so that one end becomes north, one end becomes south, so that's why I break it. So what will happen? Immediately there will be a south pole appears here, there will be a north pole appears here, like this. Okay, so this is how you cannot separate the poles of a magnet. Okay, so monopoles do not exist. Monopoles means singular poles are called monopoles. They are hypothetical things. You cannot actually have a magnetic monopole. A current carrying solenoid also behaves like a bar magnet. We have known that if you use a solenoid, okay, it also behaves like a bar magnet. So this is a solenoid, okay, and it has the same magnetic field lines are almost same as a magnet. Okay, and in between the magnetic, we already know that the magnetic field inside the solenoid remains constant. Okay, and in fact, if you put some iron filings near it, it will show that there are some points where the magnetic field is strongest, and that is the north pole and south pole. Okay, so they are the north pole and south pole of the solenoid. If you put a core such as soft iron in between the solenoid core, then definitely it will behave like a magnet, as if it is a magnet. Now let's move on. The magnetic field lines, another important concept. The magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike electric dipole, where these field lines begins from positive charge and end on the negative charge or escape to infinity. Okay, for example, if you use a positive and negative, that is a dipole, okay, linked with something, okay, here the magnetic field lines start from positive and either they go to infinity or they end at a negative. Okay, so this is the basic thing. But same thing if you try to draw using a poles, so north pole and south pole, so north pole is considered to be equivalent to positive charge. Now in this case what happens is, so magnetic field lines, they start at north pole, they end at south pole, okay, and then slowly inside the magnet it runs from south to north. Even if the magnetic field lines is not visible, it is going far away, it again comes back via far away distant. Okay, that entire path you cannot say, but it is always forms a closed loop. Okay, unlike in electric charges, there are some field lines which do not come back to negative charge at all, right? But in this case, in case of magnetic field lines, they always comes back to the south pole always. Okay, so that is why even if suppose this line in this diagram, it is shown that it is going towards infinity, but it does not go to infinity. After traveling some long distance, it comes back to the south pole. Okay, that is the basic difference between dipole and bar magnet. Next, what? The tangent to the field lines at a given point represents the direction of the magnetic given point represents the direction of net magnetic field B at that point. Suppose I have a magnetic field lines like that. Okay, so these are the magnetic field lines. If you want to find the direction of magnetic field at this point, what you have to do, you have to draw a tangent. The tangent represents the net magnetic field at that point. Okay, the larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. Suppose I have a unit surface area like this, and say 3 lines are passing. Now same area, if I consider a same area but having more number of line passing, Okay, that means it has a stronger magnetic field. So more number of lines always represent stronger magnetic field. So number of lines, concentration of magnetic field lines represents stronger magnetic field. The magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at that point of the intersection. So direction of magnetic field, we already know that the tangent drawn at the point represents the direction of magnetic field lines. Now in case two magnetic field lines cross, suppose this line and this line cross, then according to this line it will say the magnetic field is in this direction, and this line will say it is in this direction, which is not possible. So unique magnetic field is a unique quantity, it's a vector quantity, so it will only have a one direction, it cannot have multiple directions. So that is why it is impossible for two magnetic field lines to intersect each other. Easy to remember. Now let's see some formulas. Bar magnet and solenoid. So this is for this formula is valid for bar magnet as well as solenoid. The axial field of a finite solenoid or a bar magnet. So axial field means the same way you did for electric dipole, you did it for magnetic field on the axis of the dipole, right? Similarly, if you consider a large distance from the bar magnet is not as small as a dipole, so you have to consider the distance reasonably. So that magnetic field is basically given by mu naught by 4 pi, okay, into 2m by r cube. What is m? M is magnetic dipole moment. For a general magnet it is given by 2l into mu. What is mu? Mu is basically the strength of one pole. So suppose north and south. So for example, we know that in case of dipole we have plus q and minus q, right? Similarly for magnetic poles also we have mu. Okay, one, if you consider one is plus, another one will be minus. For convenience, sign is not important, but it is similar to that of the charges. Okay, so this is the magnetic monopole strength. It is called magnetic monopole strength, okay, or magnetic pole strength. Now mu is called pole strength, and pole strength for a solenoid is basically defined by NIA, National Investigative Agency. Okay, those who check for corruption in India, right? So, or terrorism in India, that is the National Investigative Agency. So all the domestic terrorism part are taken care by NIA. Okay, so they do the investigation if someone is doing some terrorist activity in India. So mu is basically NIA. That is how you can remember it. Okay, nothing to do with NIA. It is just to remember as a acronym. Okay, so NIA is basically a number of turns in the solenoid. I is the current passing through, and A is the surface area. Now if you multiply it with 2L, you get the total magnetic dipole moment. So here N is basically number of turns per unit length. Okay, number of turns per unit length, and if you multiply it with 2L, you get the total number of turns. So anyway, they are whatever formula you want to remember, that is fine. Now next, move on. The torque on a small needle. The torque acting on a small needle like this. This is a magnetic needle. When you keep a magnetic needle in the presence of a magnetic field, external magnetic field, it obviously experiences a torque similar to that of electric field, and that expression is given by tau is equal to m cross b. Okay, cross product. So m cross b or mb sin theta in scalar form, tau is equal to mb sin theta. Okay, this is the torque. M is the magnetic dipole moment, same formula as usual. Now potential energy stored in the needle, same like magnetic electric field, minus P dot E. In this case it is minus M dot B, or it is MB minus MB sin theta, cos theta. Okay, minus MB cos theta. Dot product. So always remember that scalars are always cos theta and vectors are always sin theta, if there are more than two quantities involved, that is. Negative sign signifies that work done by the field and not by the external force. So negative sign indicates that work is done by the field itself and not by the external force. That is why the negative sign. If field is doing work, it is negative. If we are doing work, then it is positive, right? Let's move on. Let's see one problem. If a bar magnet of magnetic moment M, capital M, is cut along its length into two equal parts, then what will be the change in the magnetic moment of the magnet? So we have a bar magnet, okay, north and south. Okay, now what we have done, we have cut this bar magnet into two halves along the length. Okay, so suppose the initial length was 12. Now when we cut this magnet into two halves, what will happen? An equal magnetic pole will appear on this side with south, and equal north will appear on this side. Okay, so magnetic strength is not changing, only thing that is changing is the length. So now the length of each part is L, this is also L, this is also L. Okay, now you have to calculate the change in the magnetic moment. So change in the magnetic moment is very, very important. So what is the old magnetic moment? Magnetic moment was M equals to mu into 2L. Okay, now what is the new magnetic moment? So new magnetic moment, say for this is M1. So what is the new magnetic moment? Magnetic moment is basically same mu into L. Now length is reduced, right? So length is reduced. So it will be, initially it was 2 mu L. Now it is only mu L. What is the change? Change is basically 2 mu L minus mu L, that is mu L. That is basically capital M by 2. So the change in the magnetic moment is basically M by 2. So both of them have reduced by an quantity of M by 2. Okay. Now let's move on to the next part, electrostatic analog. Here we will compare some quantities. So for example, 1 by epsilon naught is basically equals to mu naught in magnetism. Okay, the dipole moment P is replaced by magnetic moment M. Okay, and for a equatorial short dipole, it is given by minus P 1 by 4 pi epsilon naught r cube. This is entire thing in the denominator. Here it is minus mu naught M 4 pi r cube. So same thing, only P is replaced by M, and 1 by epsilon naught is replaced by mu naught. Otherwise the formula is same. Axial field of the dipole 2P 4 pi epsilon naught r cube, it is mu naught 2M 4 pi r cube. Okay, it is P cross E, it is M cross B. It is minus P cross E, it is minus M dot B. So electric field is replaced by magnetic field B. Okay, the dipole moment is replaced by M, and the 1 by epsilon naught constant is replaced by mu naught constant. If you remember one of the table, you can easily convert it into the second part just by understanding what all are changing and how. Right, so this is the important table to remember for you to answer such question. Maybe the question that you are expecting using dipoles, same question might come using magnets now, but you have to adjust the equation. Right, now if you are preparing for your KCET 2025 exam, then definitely you should aware of the Abhyas KCET test series we have launched recently, and Abhyas KCET test series is available right now in our portal. The link of this is given in the description. You have to register for it, and only by registering you can get access to the first 4 free tests that is available in our website. Okay, the link is given in the description below. Just go there, register for free, and you check all the 4 question papers. Okay, and if you want to purchase the test series, it is available for 1498 and plus 1 rupee for your PU2 test test series that we have launched quite some time back. So that is also available right now for only 1 rupee extra over and above of 14.99, right? So don't wait, price may go up, so buy right now so that you can get advantage of your KCET preparation as well as your PU board preparation. And if you just a dropper, you can purchase it for 14.98 only. Also, if you don't want to decide right now, you can take the first 4 tests for free, for absolutely free. Only thing you have to register, download the app, use the credentials provided to your registered mobile number, and you can just use the app and you can check whatever is the free test, right? So don't wait for the last moment. From 17th March onwards, it will be a full-fledged test. Okay, the test series is schedule is given in the website. As I said, link is given in the description. Okay, now magnetism and Gauss's law. So the net magnetic flux through any closed surface is 0. So if you remember, in electrostatics we have learned that E dot electric field E dot ds was given by Q enclosed by epsilon naught. Okay, but in case of magnetic field, it is coming out to be 0. Okay, why 0? So in case you wonder what will be about, what about magnetic monopole enclosed? Magnetic monopole enclosed, actually magnetic monopole enclosed is not possible. Okay, and if you consider in terms of flask, okay, suppose I have a magnet. You are saying that, sir, magnetic monopole may not be having there. What I will do, NS, I will consider the surface like this. Now I have a monopole of mu enclosed. So what about now? So you have to remember that whatever field lines that is exiting from here, okay, the same number of lines are coming from inside. Okay, same number of line is coming from inside. So that is why total outgoing flask equals to total incoming flask. So flask change is 0. So no flask is changing. No flask is changing means B dot ds is equals to 0. That is known as Gauss's law of magnetism. This is the consequence, the fact that magnetic field lines are closed and no magnetic monopoles can exist. So basically, because magnetic field lines are closed and monopoles cannot exist independently, whatever going out, the same number of lines has to come in. So magnetic flask through a closed surface will always be 0. Okay, so this is a, sometimes they ask you which of the following is a consequence that monopole does not exist, or what is the consequence of Gauss's law of magnetism. So you have to identify that magnetic monopoles do not exist. That is the consequence. Next is magnetization. A circulating electron in an atom has a magnetic moment. In a bulk material, these moments adds up vectorially and they can give a net magnetic moment which is non-zero. Okay, very important. Okay, in case of bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. It can be 0 as well. Okay, magnetization M of a sample is defined as the net magnetic moment per unit volume. It's very important. Even if the atoms are orbiting around the nucleus, atoms are orbiting around the nucleus, that orbiting orbiting electrons basically gives rise to the magnetism. Now this magnetism may present in the atomic level, but when you go to the bulk material level, one magnetism cancels other one. Okay, and there are a lot of other properties happen. For example, copper was a paramagnetic in atomic level, but as a bulk material level it is a diamagnetic material. Okay, they cannot have a bulk copper material which is paramagnetic no matter what is the temperature, because their internal structure is such, the internal bonding is such that they cannot have a electron which is orbiting independently. So that is the reason. So magnetization is very important. That is why if the magnetization itself is 0, then obviously it's a diamagnet maybe. Okay. Now magnetization M for a sample is defined as the net magnetic moment per unit volume. So net magnetic moment is denoted by small m net divided by unit volume, that is called the magnetization. This is the formula for magnetization. Okay, magnetization is a vector with dimensions L to the power A into ampere. So ampere per meter is the unit. Okay, so L to the power minus 1 into A is the dimension, ampere per meter is the unit. These are the important things to remember for MCQ, small easy MCQs. They can come based on this magnetization. Now let's move on. Magnetic field intensity, capital H. Now we will discuss about magnetic field intensity. We are talking about magnetic field. Magnetic field is generally denoted by B. Now we will talk about magnetic field intensity H. Now what is H? H is basically defined by magnetic field divided by whatever is the permeability of the medium minus magnetization. Okay, this is called magnetic field intensity. Basically this measures what is the effect of the external field on the material. Okay, the dimension of H is same as M and its unit is ampere per meter. So M is basically internal response, internal magnetization. H is basically external. Okay, that is why we are dividing it and subtracting it to understand what is happening due to the external field. Okay, now B can be written by, now magnetic field at a point is basically external field component plus internal field component. Everything has to be there. Okay, so that is why it is mu naught H plus M. Now again there is a direct relationship between magnetization and magnetic field intensity. They are related to each other. They are cousin brothers. Now they are related by this quantity chi. What is this chi? Chi is a dimensionless quantity and is appropriately called magnetic susceptibility. So how quickly, and if you apply some magnetic field, how quickly it can magnetize the material. Okay, so magnetization is basically dependent on external electric field, right? So external magnetic field. So how quickly it can adapt to the applied electric field, magnetic field is called the susceptibility. Susceptibility means how susceptible you are. So how quickly I am telling you, go and jump from the top floor. So how quickly you are listening to me and don't jump it, just a joke. So how quickly you are listening to me and following my instruction, that is your susceptibility. I know you are not susceptible to my kind of talking, but anyway, this is just a joke. Don't take it seriously. So anyway, so it is basically how susceptible you are. So whenever someone tells you, hey bro, this question will come in the exam, you go and study. Hey, you studied hard about that exam, but that question did not come. So you were susceptible at this moment because someone informed you that this question is going to come in the exam and you studied it. But if you are not susceptible, you are strong enough in your heart, you know that okay, no matter whatever question will come, I will be able to answer it because I am fully prepared. So that is the level of confidence. So magnetic materials are not that confident. They are susceptible to external magnetic field. It is a measure of how a magnetic material responds to an external field. Okay, so it measures how magnetic material responds to an external field. That's what I am talking about. Anyway, let's move on to the magnetic. Again we are continuing with the expression, that is B is equal to mu naught M dot M H plus M. Again M is chi plus A, chi into H. So now if we replace it, what we will get? We will get B equals to mu naught 1 plus chi H vector, or you can say this is basically whenever there is a material present, there will be relative permeability. Okay, or B is equal to mu H. What are all those quantities? Mu R equals to 1 plus chi is dimensionless quantity called the relative magnetic permeability. Okay, so mu R equals to, this is a very very important formula from this chapter. Based on this 2-3 questions, 1 or 2 questions might come, maybe maximum 1 question, but there is a probability that 1 question is coming, that you have to apply this knowledge to solve it. Okay, it is the analog of the dielectric constant in electrostatics. The magnetic permeability of the substance is mu and has the same dimension and units as mu naught. Okay. This is also permeability, magnetic permeability of a medium. Okay, it varies from medium to medium, and definitely it is a multiplication of relative permeability and free space permeability. Okay, now let's move on. Again, mu r is equal to mu naught into mu r or mu naught into 1 plus chi. Okay, the three quantities chi, mu r and mu are interrelated and only one of them is independent. Given the one, the other two may easily be determined. So if you say that, okay, I am fixing this value, okay, then whatever value of mu r, based on that you can calculate mu, or mu naught you already know, so based on mu naught you can calculate mu r. So mu r, mu naught, they are all, sorry, there is a mistake here. There is a mistake here. This is not mu r, this is simply mu, right? This is simply mu. So mu is basically mu naught into mu r equals to mu naught into 1 plus chi. Now let's move on to the next part, magnetic properties. There are three magnetic properties, as we all know. What are all those? So diamagnetic properties. So diamagnetic substances are those which have tendency to move from stronger to the weaker part of the external magnetic field. In other words, unlike the way a magnet attracts to a metals like iron, it would be repel a diamagnetic substance. So diamagnetic substances are repelled by magnetic field. Okay, examples of diamagnetics are superconductors at absolute zero temperature. Okay, when you get superconductors, they are perfect diamagnetic. Okay, superconductors, they actually get repelled by the magnetic field. If you have seen that a frozen puck floats over a magnetic field, that is basically it is a superconductor, and once the magnetic field is there, it is getting repelled. Okay, there are a lot of possibilities of this technology, but it is not yet practicalized right now. But maybe in future you will be someone who will develop some technology and we will be able to travel faster using that technology, maybe. Right, and if you see that the magnetic field lines, instead of getting inside the material, it is getting repelled and moving outside the material. Okay, this is how it is getting repelled. But repulsion is very weak, not super strong repulsion. This is very weak kind of repulsion. Next, the simplest explanation for magnetism is follows. Electrons in an atom orbiting around the nucleus possesses orbital angular momentum. These orbiting electrons are equivalent to a current carrying loop and thus possesses an orbital magnetic moment. The diamagnetic substances are the ones which resultant magnetic moment in an atom is zero. Okay, when magnetic field is applied, these electrons having orbital magnetic moment in the same direction slow down, and those in the opposite direction speed up. So basically we know that all the electrons are rotating in an atom, right? And when the electrons are rotating in the atom, they already have a dipole moment, magnetic dipole moment. But because they are rotating in one direction and opposite direction, they basically align themselves such that they cancel each other. Now in case of external electric field, whoever is opposing the electric field, that field gets stronger, and whoever is supporting that electric field, that gets weaker. That is why it gets repelled. That is the basic meaning of this entire lineup. Okay, so the magnetic field applied, those electric having orbital magnetic moment in the same direction of the direction slow down. So basically whoever is supporting the external magnetic field, they are slowing down. Whoever was opposing the magnetic field, they are speeding up. So that is why they cancel, the external magnetic field repulsion becomes more prevalent, right? Now before going into paramagnetic, I should also want to remind you one more thing. This is a property of all materials. All materials have some sort of diamagnetic property, which is common amongst all types of material, diamagnetism. Okay, now based on the paramagnetic or ferromagnetic that we are going to study next, those two are stronger. If those two are stronger than diamagnetism, then diamagnetism gets suppressed. Okay, and they do not they were not able to come up to the ground. So basically what this does mean that all of us are basically not ready to study. no matter is the class topper, no matter is the backbencher. Okay, our inherent property is not to study. We always reject the books. Now sometimes our attraction towards the books is getting repelled by the repulsion, so that's why it is overcome. So that's why someone becomes topper, someone becomes backbencher, right? So if you think that okay, I don't want to study, I don't want to open book, don't worry, that is the inherent nature. Okay, that is that nature gifted you. Now if you can overcome that, then you will become a successful man. Okay, nature does not want you to be successful. That is the basic thing. Nature wants you to go to the jungle, hunt for animals and eat. That's how we used to do it long time ago. Now we overcome that. Now we have built our own houses, we eat whatever we want, right? We want vegetarian, so we eat vegetarian. Okay, but nature does not want you like that. Nature wants you to go to the jungle, hunt like an animal and eat, right? So that's just a joke, but you have to understand it, the meaning of it, so you don't forget it in the exam. Now magnetic properties, next part is paramagnetic. Paramagnetic substances are those which gets weakly magnetized when placed in an external magnetic field. So they are the substances here exactly opposite to the diamagnetic magnetic proper substances. They gets weakly attracted. So diamagnet gets weakly repelled, they get weakly attracted. They are not yet the good students of the class. They are trying, but they are scoring average but not super good. Okay, so they have the tendency to move from a region of weak magnetic field to a strong magnetic field. That is, they get weakly attracted to a magnet. Okay, as you can see that previously magnetic field lines were going out, now the magnetic field lines are slowly going in. Okay, now next is ferromagnetic. This is the class topper. They are the toppers of the class. Okay, they are super strong. What is the ferromagnetic materials? Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. So whenever I am teaching something, trying to explain you the concepts, you are understanding everything in detail, in depth, then basically you are a ferromagnet. Okay, they have a strong tendency to move from a weaker region of the magnetic field to the strong magnetic field. That is, they get strongly attracted to a magnet. Okay. Now ferromagnetic material does not end here. The individual atoms or ions molecules in a ferromagnetic material possesses a dipole moment as in the paramagnetic material. So paramagnetic material and ferromagnetic material, they both possess a permanent dipole moment. Okay, diamagnets, individual atoms have dipole moment, but they can cancel each other and net dipole moment is 0. Okay, now however, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. Okay, now in case of ferromagnets, they are not only restricted to the atoms. That is the basic difference. Okay, in case of ferromagnets, they are not restricted in only in the atoms. What they do, their relative magnetic moments, okay, atomic magnetic moments, they align in a particular region. They all align in a particular direction. Okay, for example, if you have seen that some toppers in the class, they are sitting in the first bench, they are discussing some problems, some questions amongst themselves. Okay, so there are some toppers in the other side, they are also discussing and answering some questions. So they are the rivals of this other group, right? So they always try to come up first in the exam. So that is how the domains are formed. Okay, maybe there are domains in different sections as well. Okay, so toppers in this class, they do not talk to the toppers of the other class. So these are all the small student life jokes that I used to give you. Now next is, if you see that here, as you can see, instead of having atomic domain, we have a small area. this area, they contain lots of atoms. Okay, they may be containing thousands of atoms. All the atoms basically are rotating, electrons are rotating such that they all are aligned in the particular direction. Okay, so these zones are having, instead of having molecule wise or individual atom wise, all the electrons in these particular zones, they are rotating in the same direction, so that they have a dipole moment in a particular direction. These small areas are called domains. Okay, they are called domains. Now if you apply external magnetic field, okay, domains generally align in a particular direction, giving you the magnetic field, induced magnetic field in this, right? Now domains are not perfectly aligned. They have, if you see even in the diagram, domains are not perfectly aligned. They have some distortion in their alignment as well. Okay, now what happens when the external field is removed? Now if you remove the external field, so under the influence of external field, domains have now aligned. Okay, now if you remove the external field, what will happen? In some ferromagnetic materials, the magnetization persists. Okay, such materials are called hard magnetic materials or hard ferromagnets. Alnico, an alloy of iron, aluminium, nickel, cobalt and copper, is one of such material. So alnico is a hard ferromagnet. Okay, hard ferromagnetic material or hard magnetic material. Okay, even if you remove that, it will still remain as magnet. The naturally occurring lodestone is another. So lodestone is also another example where it gets a lot of times staying under the magnetic field of earth. Okay, lodestone is a particular ore available under the ground. So if you are digging something, and there was a story that some shepherd found the first magnet. He was herding his sheep in a ground. Okay, and then he took his stick into the ground. His stick struck to the ground because his stick had a iron ring around the bottom of the stick. That ring stuck to the ground, and then he discovered lodestone. That was how the story goes. Okay, now such materials from permanent magnets to the used among the other things as compass needles. So they are used as permanent magnets. If you have done experimentation in your PU2 lab using magnet, they are basically permanent magnets made of some hard magnetic materials. Okay, and also they are also used in the compass needles. So if you have seen compass needles from ancient times, compass needle is used to find the direction. So compass needle is also used, ferromagnets are also used to generate compass needle. Now what happens when the external field is removed? Now let's look into some other materials. There is a class of ferromagnetic materials in which the magnetization disappears on removal of the external field. So we have learned about hard ferromagnetic materials, right? There are some soft ferromagnetic materials. They lose their magnetic properties once the external magnetic field is removed. One such example is soft iron. Soft iron is one of the example. Even if you remove the magnetic field, it loses its magnetic properties almost immediately. Okay, appropriately enough, such materials are called soft ferromagnetic materials. Okay, there are a number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, etc. They are the examples. Now soft ferromagnetic materials also have a lot of applications. Okay, for example, hard ferromagnetic materials, they are used in permanent things. For example, permanent magnet, magnetic compass needle, whereas soft ferromagnets are used in transformer cores. They are used in solenoid cores to make electromagnets. So in electromagnet transformer cores, soft ferromagnetic materials are used. Okay, the relative magnetic permeability is more than 1000. So relative permeability is more than 1000 for a ferromagnetic material. Now let's see one table. Okay, so for diamagnetic, as you can see, magnetic susceptibility chi is basically it is negative. okay, but slightly negative, not super negative, okay, greater than -1, greater than equals to -1, but it is less than 0, okay, and relative permeability is greater than 0 but it is less than 1, so it is positive but small, and mu is less than that of mu naught, okay, very important. Now in case of paramagnetic material, okay, as you can see that it is positive but very slightly positive, okay, here epsilon is basically small positive number. Why it is written like that? So basically the relative permeability is basically starts from 1 and it is less than that of 1 plus epsilon. That is why they have written it like this, and obviously mu is greater than mu naught. In case of ferromagnetic material, chi is very greater than 1, mu r is also very greater than 1, and mu is also very greater than mu naught. So these are the basic difference table. You can remember it, or in the exam hall based on the data provided to you, maybe the mu value is very small but it is positive. In that case you will understand this must be a paramagnetic material, okay, sorry, not mu, susceptibility. Chi is given very small but positive, then you can know, okay, small susceptibility means it is must be a paramagnetic substance, negative susceptibility means it must be a diamagnetic substance, right? Very high susceptibility means it will be a ferromagnetic substance. This is how you can determine. Now if you also want to, if you are interested in the Abhyas KCET test series, let me talk about it in detail. So what all you will get 35 tests, okay, out of the 35 tests 4 free tests and 31 paid tests. For free test you have to use the link given in the description, register for free, and then you can get the first 4 free part test available in our channel, not in our WhatsApp channel or in YouTube channel. This is a completely different portal. Through our app you can download the app and you will get the 4 question papers, okay. Now here you will get full syllabus chapter wise tests, okay, detailed video solution and analysis. You will also get chapter wise one shot revision videos. You will get chapter wise insight for last 5 years of KCET paper. So how last year KCET paper, which paper has changed, which subject has changed, so everything will be at one place. You can check that out. The link is given in the description, and the price for this is 1498 for only the test series. If you add 1 rupee extra you will get 1499. Absolutely, for 1 rupee you get the PU2 test series, okay, which was launched almost 2 months back. So that you can get almost for 1 rupee only. And if you are preparing for your PU board and KCET board, this is the must have course for you, okay. And I will be back with a more video in our coming days. Till then, bye. And if you have not yet subscribed to our channel, don't forget to subscribe, give it a thumbs up and share it with your friends. Thank you.